Doctor, I'm really not feeling well. I need your help.
Nurse, I think we better prep this guy for surgery. We're gonna have to take his appendix out.
Sure thing, Doc.
Wait, what?
We'll try that. If it doesn't work, we'll try something else.
Have you ever had a power quality problem and you felt like people were just suggesting solutions haphazardly, like a UPS or a surge protector, to see if they could work? It's very similar to the doctor analogy. You have to identify the symptoms of the problem before you can solve the problem. We say, identify the symptoms, determine the source of the issue, and recommend the right solution to correct the problem. This is the most expedient and cost-effective method to solving any power quality issue, and really any problem.
By the way, what symptoms do you have?
Well, I've been feeling dizzy and I've got some flu-like symptoms, and it all started when I got this bullseye rash on my stomach.
That sounds like Lyme's disease. Were you bitten on the stomach by a tick?
Mm-hmm.
Nurse, scratch that appendix thing. I think he's got Lyme's disease. We'll confirm that with a Lyme's test, and then we'll administer a prescription for doxycycline.
Sure thing, Doc.
Here at the Power Systems Experience Center, we can reproduce almost any power quality issue you can think of. In this video, we will give you some examples of real power quality situations and help you figure out what the symptoms are telling you so you can identify the problem and implement the right solution. Power quality is defined by the IEEE as the concept of powering and grounding electronic equipment in a manner that's suitable to the operation of that equipment. Basically, that means what works for you and your equipment. Every system and many loads are different and respond differently to PQ issues, but power quality issues can be simplified by dividing them into four main categories: voltage variations like sags or interruptions, transients or surges, harmonics, and grounding. Along with these main categories, monitoring and analysis must be done to solve any PQ problem. Monitoring may be as simple as a person indicating PQ symptoms, like the lights flickering, but it's best if done with today's modern power quality meters. Analysis may be an engineer evaluating meter data or even performing computer simulations, or today, maybe AI software looking at waveforms and making a determination. Every problem can be solved with the right clues, but sometimes clues lead you down the wrong path. If you rely on someone's memory of an event, they might say something like this.
Well, I think it was 4 weeks ago when we lost our stamping press. And I think it was on a Thursday because that's the day I usually bring in donuts, and I remember having a donut that day. No, wait, or is that the week that I traded with Jim? Anyway, I think it was on a Thursday, and it was definitely in the morning. Maybe.
With today's metering systems, you can tell exactly when something happened. Selecting the right monitoring equipment and waveform analysis are critical to understanding PQ issues. Now let's take a look at some real examples of PQ issues and how we identified the symptoms, sources, and solutions to solve those problems. Ryan, did I ever tell you the story about the bad noise and the evil noise?
No, I think I would have remembered that.
It went something like this. An offshore rig was having a problem and they called us in to analyze what was going on. I remember them saying, "We'll pick you up in New Orleans and we'll drop you off on the platform. Then we'll return with a helicopter when you fix the problem." It was kind of an uncomfortable feeling, but we got there with our PQ instruments in hand and we asked them what the problem was. I remember them saying, "Well, it's not really one problem. We kind of have two problems, a bad noise and an evil noise." I remember Martin, who was standing next to me, he looked at them and he said, "I don't think you need a PQ guy, I think you need a priest."
So what did you figure out?
Well, after we settled in and performed some measurements, what we found was a harmonic resonance problem created by a poorly designed harmonic filter. Instead of reducing the harmonics, the filter actually amplified the harmonic currents and created a 5,000 amp pulse of current through a large inductor on the platform. The sound was a consistent thump, 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 which resonated throughout the platform. That was the bad noise. Then when the current got severely distorted and the voltage got distorted even more on the generator bus, the generator's regulators actually couldn't synchronize the operation of the generator with a 480 volt bus, and the generator actually slipped a pole and created the evil noise. It was like thump, 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 bam. And it was pretty scary. You know, after all, electrical equipment really isn't supposed to make noise, especially not that kind of noise. When it was all said and done, We helped the oil company redesign the filter and resolve the problem. We captured some pretty great waveforms and learned a lot about harmonics, but most importantly, they came back to pick us up on the platform. We've seen many harmonic issues, but the bottom line is this: harmonics are not a problem unless they are a problem. What does that mean? Because it's much easier today to measure harmonics and see waveforms, people often jump to the conclusion that all harmonics are bad and all PQ problems are harmonic problems. However, harmonics on the power system are the new normal. Harmonics can create two fundamental issues: current distortion, which has the symptoms of equipment overheating, audible noise, and/or nuisance tripping of protective devices. And the second issue is voltage distortion, which typically causes misoperation in equipment. Either or both problems can cost you money with damage or misoperation to your equipment, but every system is different and careful analysis and consideration must be made, or you could significantly overspend on a perceived problem that may or may not exist. So what causes what? Well, in this case, harmonic currents cause harmonic voltage distortion. The amount of voltage distortion depends on how much current distortion is produced, or how many nonlinear loads like VFDs, computers, or other electronics you have, and the amount of impedance upstream of that current. Usually the most significant impedance is in the nearest upstream transformer, but can be increased significantly when operating on a generator. I remember one case where a financial company wanted to save some money, so they put a bunch of small single-phase standby UPSs under every desk in an office building and purchased a 40 kilowatt generator to back up the UPSs. Their incoming service transformer was much larger than the generator, so the effective impedance was much lower on the utility than running on the generator.
So why was that a problem?
When the power went out and the generator came on, the UPSs went back to normal, but they began to recharge the batteries and created a lot of harmonic current distortion. The voltage distortion on the 120 volt UPSs went from 3% distortion on the utility source to nearly 22% distortion on the generator.
Wow, isn't that high for voltage distortion?
Yes, extremely high. The UPSs determined that that wasn't a good or acceptable voltage and transferred back to battery. Once enough of the UPSs went to battery, the voltage cleaned up again and the UPSs decided the voltage was okay, so they went back to the generator source. Again, when enough UPSs came on and began charging batteries again, the cycle repeated until the UPS batteries died and the load was dropped.
So what did you figure out in that case?
Well, the symptom of the problem in this case was the misoperation of the UPSs, and in fact they were also the source of the harmonics interacting with the high impedance of the generator. The solution was to design and build two harmonic filters, third and fifth harmonic filters, so that the voltage distortion was limited to a similar level no matter which source the system was running on. Transients or surges are short duration, high voltage events, subcycle events, and their effects can be significant and damaging. Instead of the insulation of a transformer or motor looking like it was baked from harmonics, it will typically have a simple pinhole in the insulation, usually near the end turn. Transients usually result in damage that's hard to recover from. Often the equipment must be replaced. The solution for transients is usually surge protection, but surge protection is an insurance policy against that lightning strike that might happen, or that utility switching event that could occur, so oftentimes we go without protection. Today we live in a throwaway world. If you buy a $60 DVD player, you aren't going to take it to someone to get it fixed for $100. If it stops working or is damaged by a surge, you'll likely throw it away and get a new one. Surge protection offers a great insurance policy for the thousands of dollars of electronics in our homes and businesses. Multiple levels of protection are often required because transients may come in your front door, think lightning, or may come from loads like your garage door opener or your AC unit. There are many other considerations to evaluate, including grounding and SPD lead length that we discussed in detail here at the PSEC. How can you identify the symptoms, sources, and solutions for surge events? Let's take a look at some examples.
Is it true that grounding is related to surge protection?
Yes, absolutely. Surge protection and grounding are closely related. There was a case several years ago when lightning hit behind one of two buildings that we occupied in a hillside in an industrial park near Pittsburgh. During that event, $80,000 of phone equipment blew up and had to be replaced. The phone equipment was in the middle of the building and there wasn't a hole in the roof, so what happened? Well, it turned out that after analyzing the problem, we found that the lightning likely hit the hill behind and to the side of one of the buildings. When that happened, that impulse of current entered the ground and caused a high voltage gradient near our two buildings.
Is there an easy way to describe a lightning strike like that?
Yeah, it's kind of like dropping a stone into a mud puddle. When the current enters the ground, there's a high potential from that center point to the first concentric ring, maybe 200,000 volts. Then each ring to the next, there's a reduced voltage gradient, and from ring to ring, maybe it's 50,000 volts, 30,000 volts, 10,000 volts. So the problem is it would have been okay if our buildings were connected to the same ground system, but the only thing that connected those things together was the phone equipment. Ideally, think about like a bird on a wire. If a bird lands on one wire, it assumes the voltage of that wire. In the same way, if each of the buildings rose to the potential of the ground system, each would have been okay. But by tying the telephone grounds and the power grounds together in one piece of equipment, the phone equipment, that was the spark over, and the discharge, well, it's kind of like if you rub your feet on carpet and you build up a static discharge. You know, when that discharge occurs, you have a spark, but in this case, the spark caused a flashover, and then the 60 hertz current came through with a fault current and blew up the equipment.
So how did you solve that kind of issue?
Well, in this case, there were really three potential solutions. One, you could completely isolate the systems by using fiber optic phone lines. The second was really join the systems together like you would in a substation or, a data center ground grid. And then finally, apply surge protection on the power and on the communication or phone lines. Many times we forget that transients can come in on our phone lines or TV cables or really any other communication lines and damage our electronics.
I've heard that 80% of transients come from inside the facility. Is it true that all externally caused transients are from lightning?
Lightning is often considered the most significant source of surge or transient events coming in from outside your facility. However, other transients are often initiated on the utility side of the meter and can be disruptive at a minimum or very damaging depending on the magnitudes of the transient. In this example, a hospital had installed power factor correction capacitors but had no idea that the installation had created a unique situation where the voltage transient from switching an upstream utility capacitor bank would cause havoc in the hospital. Much of the modern electronic equipment we use in hospitals rely on clean sinusoidal voltage. But in this case, when the utility switched their substation capacitor every morning for volt-var compensation, the hospital saw a significant transient on their 480 volt system as a result of their own capacitor amplifying the transient. This unique situation results when the transient impedance is coincidentally similar to the frequency of the switching transient of the utility cap bank. Normally, a utility cap bank will cause a short overvoltage, maybe on the order of 1.2 to 1.6 of the normal peak. With a cap on the low voltage system, the maximum transient could exceed 4 to 5 times or more.
So did you just apply a surge protector?
No, in this case, it required some detailed analysis. The symptom of the case was the misoperation of MRI and CT scanners when the switching occurred, causing disruption and sometimes physical damage. The source was the utility cap switching, but it was related to the low voltage cap in the hospital. We've seen this in other facilities like refineries and industrial plants using power factor correction caps. The solution was either remove the low voltage cap or make it into a detuned filter to move its resonant point so that it wouldn't amplify the transient. Voltage sags are considered the most costly power quality event and the most common voltage variation, much more frequent than full interruptions on a typical power system. We've had many visitors tell us that they've lost hundreds of thousands, even millions of dollars as a result of voltage sags. When evaluating voltage sag issues, identify the magnitude of the retained voltage, the duration of the event, and the number of phases affected for historical data at the site. Of course, there are no guarantees that those events will repeat, but with enough statistical data, like this ITIC curve, you can feel pretty comfortable that you understand the issue. Then you can select the size and type of the solution for your system. These solutions range from small ride-through devices through large UPSs and everything in between, each with different technical advantages and cost benefits.
Why are sags considered the most costly PQ event?
Well, basically because they generally affect a majority of your facility or process. Here's an example. A 7x24 plastics plant was very diligent about monitoring their power system, and they had identified the fact that over the past 5 years, they averaged 14 deep voltage sags that caused disruption of their facility. Only one of the 14 on average was a full interruption. They also identified the fact that they lost $30,000 per event as a result of the seized equipment and the associated cleanup after the event. The 13 sags had a typical range of 60 to 75% retained voltage, and a sag over 80% retained voltage wouldn't disrupt their process based on their data. So with that information in hand, we helped them identify a solution, a sag corrector, which would cost them about $500,000.
Wow, that's pretty expensive.
Yes, but based on the simple payback, the sag corrector could pay for itself in 1.3 years. Everything seemed to be going smoothly when the plant manager decided to stop the project. His answer was, "We've been building up our inventory, so we don't have to worry about losing out on sales." What he failed to recognize was that the cost of their inventory was basically replacing the cost of their losses from sags. Later, when we asked again about the project, they said, "We aren't doing anything at this time because we intend to double the size of the plant because we can't keep up with production, and we can't afford to spend any capital on this solution." Again, another common issue in PQ resolution. Whether it's capital or expense money, PQ issues cost you money. Now potentially 2 times the losses for this plant.
Sounds like they should have listened to you. Do you have a good example of an oil and gas company affected by voltage sags or interruptions?
Yeah, absolutely. In one case, we evaluated a large oil field in Central America, and we looked at solutions for variable frequency drives on progressive cavity pumps that were dropping out during deep sags and interruptions from recloser operations. Sometimes utility companies use reclosers at their substations and on their distribution feeders to clear temporary faults like lightning or tree contact. Then they reset the line after the temporary fault is cleared. By doing this, they don't have to send a utility truck and a lineman out to change a fuse cutout. However, if the fault's permanent, the fuse can blow and the system's coordinated.
So how does a progressive cavity pump work?
A PCP pump or a screw pump is essentially like an auger that draws the oil from 4,000 feet below the surface, and it takes about 4 hours to get this heavy crude from the bottom to the top. During a recloser operation, the drive in the pump would stop, and it would take about 4 hours to backspin the 8-inch shaft, and then 4 hours to pull the oil back up to the top. In other words, they'd lose 8 hours of production for an event that lasted 1/10 of a second during a recloser. So we considered mechanical solutions involving stopping the backspin of the shaft, but the risk of damaging or breaking the shaft was significant, and the cost of pulling the damaged shaft was on the order of $1 million.
So what did you do?
After we evaluated many solutions, we determined that the best solution for the payback was an ultracapacitor ride-through device connected to the DC bus on the drive that we called a DRT, or drive ride-through. The DRT provided about a 2-month payback, and it was the ideal solution for this power quality issue by allowing the drives to ride through the recloser operations. Identifying the symptoms and sources of your issues are key to determining the right solutions to your power quality problems. Monitoring and analysis ensure that you determine the most cost-effective solution. Here at the Power Systems Experience Center, we can reproduce almost any power quality issue and simulate things that you're seeing on your system. Let us help you identify the right solution for your power system. Contact us or your local Eaton representative to schedule a visit to the Power Systems Experience Center today.